All right, for our last lesson before the AP exam, we're going to take a look at section 12.2. We're going back to regression and looking at transforming data to achieve linearity. So, first, let's take a look at this graph. We are looking at income per person versus the lifetime expectancy of people in various countries around the world. The circles, the size is based on the population of the country, and the colors are based on the region, which you can see in the key. Now, clearly, this is not a linear graph. There is a distinct curve. So, doing linear regression, like we discussed earlier in the year, isn't going to work exactly the same. We have to do some adjustments first. So, if you go back and look at this graph, this curve somewhat resembles a logarithmic curve. It starts off really steep and flattens out. So, we can use logarithms to straighten out this data. So now if you look at the axes, our x-axis is log of income per person. Our y-axis is still the life expectancy. But now our data is much more linear than it was originally. Now that the data looks linear, you can do linear regression like we discussed earlier in the year. And that's the basic idea of today's lesson. So, applying a function, such as a logarithm or a square root, to a variable is called transforming the data, or sometimes you'll see it called re-expressing the data. And it changes the scale to make the data look more linear. So, the first situation we're going to consider is a power model. You have y equals a times x to the p, where p is any power. We can transform the data. So instead of looking at x and y, we can look at x to the p and y, and that will make it a linear form. So let's look at this example to see what I'm talking about. Imagine you've been put in charge of organizing a fishing tournament for which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat probably not going to be very accurate. It would be much easier to measure the length of the fish while on the boat. What you need is a way to convert length to weight. You contact a nearby marine research laboratory and it provides reference data on the length in centimeters and the weight in grams for Atlantic Ocean rockfish of several sizes. And we have the data and the scatter plot here. If you look carefully, there is a slight curve to the data when you are comparing just the length and the weight. Because the transformation made the association roughly linear, we used computer software to perform a linear regression on y equals weight versus length, or x's length cubed. The reason we chose to cube the length is because we're going from a one-dimensional measurement, length, to a three-dimensional measurement, which is weight. So going from length to volume, your best bet is probably cubing it. And you could do some trial and error in a spreadsheet to make sure that, yes, cubing it is a good exponent. So we want to give the equation of the least squares regression line using this output here. So if you look at the top of the box, it says we have weight versus length cubed, so it tells us we're doing length cubed. And if you remember back to when we did regression, if you look at the constant line, this first number is going to be our y-intercept, and at the next line, length cubed, this first number is going to be our slope. So, when we write out our equation for the least squares regression line, a couple things to remember. It tells us to define the variables we use. So we just use the words length and weight. Our y-intercept is 4.066. Our slope is 0.0146774. Don't round it. And remember that in this case, our x is length cubed, not just length, and our y is weight. And if you remember, this hat means we're looking for the predicted weight. Every time you are doing one of these problems, you need to have the hat over whatever your y variable is. And that's our least squares regression line. Part B says, suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Use our model in Part A to predict the fish's weight. Well, the length is 36 centimeters, so we just plug 36 in for length. Do the math, and you get the predicted weight is 688.6 grams. And that's it. Now, let's go back to our power model, y equals a times x to the p. If we look at a scatter plot here, and again, we're looking at the fish, length cubed and weight, our x to the p paired with y gives us an approximately linear scatter plot. But you could essentially get the same effect by looking at length and cube root of the weight. That will also produce a linear scatter plot. So having x to the p, y, is equivalent to using x pth root of y. So let's look at that situation. Same deal, we have this fishing competition looking at Atlantic Ocean rockfish. This time we are looking at length and the cube root of the weight. So y is the cube root of the weight, x is the length. We have a new computer output. Remember, this is your y-intercept, this is your slope. We want to give our equation for the least squares regression line. Make sure you correctly define your variables. Your y is cube root of weight. Remember, you have that hat for predicted. We have our y-intercept, our slope, and our x variable is the length of the fish. We're using these two numbers for the y-intercept and the slope. Then part B says, suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that is 36 centimeters long. Use the model to predict the fish's weight. So, plug 36 in for the length, do the math, and here's the thing you got to be careful about. You are solving for weight, not the cube root of the weight. So you do have to cube both sides to get back to your final answer for the weight of the fish, which is 694.6 grams. Now, I'm going to flip back real quick. That's very close to the answer we got in the last example, but a tiny bit off. So that's 694.6. This was 688.9. So it's not going to give you the exact same numbers, but it should be very close. Both transformations, either cubing the length or taking the square root of the weight, will result in linear scatter plots with very similar linear regressions. Okay, so that's one way to achieve linearity. You could raise x to a power, or you could do some root of y. Either one should give you a linear scatter plot if you're working with a power model. What if you have no idea what value of p to use? You try squaring, cubing, raising to the fourth power. You don't know which is best. Well, another option is by taking the log of both x and y. And this comes from some properties of logarithms. So if I have my power model, y equals ax to the p, and I take the log of both sides, I can then do some properties of logarithms on the right side to rearrange this. I can split it up to be log of a plus log of x to the p, and then bring that exponent down in front. So I have log of a plus p times log of x. So if you look at this, we have log of y equals, this would be our y-intercept, this would be our slope, and then we have log of x. So we end up with a linear relationship between log of x and log of y. And you don't have to just use log, you could use natural log as long as you have the same base on both sides of the equation. So, still looking at these fish. Based on geometry, we chose the power of 3. So the weight equals a times the length cubed. So if we go back to the beginning, look at our data. Now, if I take the log of both the length and the weight of these fish, I have a pretty linear scatter plot. Remember, another way of looking to see if that is linear is by looking at the residual plot. So if I make a residual plot based on this situation, I get a scatter plot with no pattern, which is what we're looking for in a residual plot. So, based on this output, why is it reasonable to use a power model to describe the relationship between weight and length for the Atlantic Ocean rockfish? Well, going back to the residual plot here, when we took the log of both length and weight, did the linear regression, and then did the residual plot, we do not have a pattern, which means that that is a good model for that data. And because we know taking log of both the x and y variable is a way to make a power model linear, we can assume that a power model is reasonable. Part B, give the equation of the least squares regression line. Okay, again, we have our computer output here. We have our y-intercept and our slope. Make sure that you put log of length and log of weight, because we're basing this on taking the logarithm of both the x and the y variables. Again, because this is our predicted value, we need to have a hat. Part C, again, we have a rockfish that is 36 centimeters long, and we want to predict its weight. So you plug 36 in for x, do all this math on the right side of the equation, and you get 2.8464. Then we need to do some algebra and solve for weight, because right now we have log of the weight equals 2.8464. So to get rid of the log, we convert it to an exponential, and we have that the weight is going to be 10 to the 2.8464 power, which gives us 702.1 grams. Again, this is fairly close to our other estimates, but this is a little bit higher. Let's continue. So, what if x and y are actually an exponential situation? We have y equals a times b to the x power. Well, if you look at the log of y versus x, that should give you an approximately linear association. Again, using exponent rules. So if I start with my exponential model, y equals a times b to the x, I take the log of both sides, because we're doing algebra, you got to do the same thing to both sides. Use my properties of logarithms on the right side. Split it up, so I have log of a plus log of b to the x. And bring my exponent out in front. Here I have log of y equals log of a is our y-intercept. I have x times log of b. So log of b is my slope. So I'm comparing x and log of y. So, different scenario here. Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. Here are data on the dates and number of transistors for Intel microprocessors, and a scatter plot that shows the growth of the number of transistors on a computer chip from 1971 to 2016. You'll notice that we use years since 1970 as our x value instead of the year itself. So, if Moore's law is correct, then this should be an exponential model. So, here's a scatter plot of the natural, or the base E, logarithm of the number of transistors on a computer chip versus years since 1970. So we have years, log of, or natural log of the number of transistors. So based on this graph, why would it be reasonable to use an exponential model to describe the relationship between the number of transistors and years since 1970? Well, we used the transformation that is known to linearize exponential data. So, since our graph is fairly linear, there's a little bump in the middle, but it's basically linear, using the transformations that we know work for an exponential model, that means an exponential model seems like the appropriate model for this data. Here we have our computer output. We want to write the equation of the least squares regression line. Again, our y variable is the natural log of the number of transistors. We have our hat because that's our predicted value. We have our y-intercept and our slope. And our x variable is years since 1970. Part C. Use the model from Part B to predict the number of transistors on an Intel computer chip in 2020. Remember that our x variable was years since 1970. So 2020 is 50 years after 1970. So we simply plug 50 in for x. When you do that, you do the math for the right side of the equation, and then you have to solve for the number of transistors. So since we used natural log, we have to do e to the 24.9372 power to get our final answer. So this model predicts that an Intel chip made in 2020 would have about 68 billion transistors. Now, suppose we have a scatter plot with a curved relationship between x and y. How do we decide whether a power model or an exponential model is better? Let's look at this example. On July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. They had first observed this object almost 2 years earlier using a telescope at Caltech's Palomar Observatory in California. Originally named UB313, this potential planet is bigger than Pluto and has an average distance of about 6.3 billion miles from the Sun. For reference, Earth is about 93 million miles from the Sun. Could this new astronomical body, now called Eris, be a new planet? At the time of the discovery, there were 9 known planets in our solar system. Here are data on the distance from the Sun, the period of revolution of those planets, along with a scatter plot. Note that distance is measured in astronomical units, or AU, which is 1 AU is the distance from the Sun to the Earth, which is 93 million miles. There appears to be a curved relationship between distance from the Sun and period of revolution. So, how long it takes for a planet to revolve around the Sun, which is the equivalent to 1 year on that planet. So, we have 2 graphs here, looking at 2 different transformations. On the left, we are looking at distance in AU versus the natural log of the period. On the right, we have the natural log of distance versus the natural log of the period. Based on these scatter plots, would an exponential model or a power model provide a better description of the relationship between distance and period? Well, start by looking at which scatter plot is more linear. Clearly, the one on the right is approximately linear. The one on the left still has a strong curve, which means that the transformation on the right is better. So in that one, we took the natural log of both the distance and the period. So if you remember back to what we talked about a few minutes ago, taking the natural log of both x and y was a transformation for the power model. So the power model is going to be a better fit. Part B, here is our computer output when you're looking at natural log of both distance and period. So when we write our equation, we have natural log of the period, hat, because that's our predicted value, equals y-intercept plus slope times the natural log of distance. Part C, use your model from Part B to predict the period of revolution for Eris, which is about 68.05 AU from the Sun. So you plug 68.05 in for x and do the math. Do the math on the right side, you get 6.33. Then you have to solve to get rid of the natural log. I apologize, there is a typo here. Since this is natural log, this should say e to the 6.33 power, but the calculation is correct. The period would be about 561 Earth years. Part D. Here's the residual plot for the linear regression in Part B. Do you expect your predictions in Part C to be too large or too small? Or just about right? So, if we look here, the natural log of the distance, if I go back, natural log of the distance. We want to see what natural log of 68.05 is, which if you type that in your calculator is 4.22. So we're looking on this end of our residual plot. These points tend to be above the line, have a positive residual. Remember that the residual is the actual value minus the predicted value. So if our actual minus predicted is greater than 0, that means that our actual year on Eris is greater than our predicted value, which means our prediction is probably too small. And that's it. That is our last lesson of the year.